Welcome to our presentation on multithreading model. In this presentation, we'll see about its objective, types, comparison table and real-world example. Myself Nandini along with my team members Janani and Shravanti. Now I'll explain the concept of multithreading, which is a fundamental paradigm in concurrent and parallel computing architecture. Multithreading refers to simultaneous and coordinated execution of multiple threads within a single process, where each thread represents an independent sequence of instructions sharing the same memory context. This mechanism allows for fine-grained parallelism, enhanced computational efficiency, and improved responsiveness in software systems. The primary objective of multithreading is to maximize processor utilization through concurrent task execution, thereby reducing context switch overhead, minimizing latency, and achieving optimal throughput across multi-core and multiprocessor environment. It aims to leverage hardware-level parallelism while ensuring logical consistency and synchronization among threads. Now let's see the types of multithreading model. The first one is many-to-many multithreading model, which is an advanced threading approach where multiple user threads are mapped to multiple kernel threads. This allows several threads to execute concurrently while maintaining flexibility and efficient CPU utilization. In the diagram, imagine a set of user threads at the top and kernel threads at the bottom, connected through a dynamic mapping system. Each user thread can be linked to any available kernel thread. The main advantage is that it provides true parallelism and avoids blocking problems seen in many-to-one model. It's also more scalable and resource efficient than one-to-one model. However, its drawback is complex management. Maintaining synchronization and mapping between threads requires sophisticated control.
I'm Janani. I'm going to say about the many-to-one model. In this model, many user-level threads are mapped on a single kernel thread. Thread management is handled by the thread library in the user space, and the kernel is unaware of the presence of multiple threads. The thread library schedules threads in the user space. When one user thread makes a system call, the entire process blocks. Since only one kernel thread exists, true parallelism on the multiprocessor system is not possible. In the diagram, we can see a kernel space and a user space. N number of user threads are mapped on a single kernel thread. The pros: thread creation, switching, termination are quicker since kernel involvement is minimal. No kernel mode management reduces system overhead. Works even on system without native multithreading support. The cons: even if the system has multiple CPUs, only one thread runs at a time. If one thread performs a blocking system call, all the other threads are paused. The scheduler cannot interrupt a misbehaving thread since scheduling is done in the user space. The next is the one-to-one model. Here, each user thread is mapped on a single kernel thread. This means that for every user thread created, an operating system creates a corresponding kernel thread. When a user thread is created, the OS also creates a corresponding kernel thread. The kernel handles scheduling, synchronization, and context switching. If one thread blocks, other threads continue execution. In the diagram, we can see n number of kernel threads and user threads mapped to each other. Pros: multiple threads can run simultaneously on different CPUs. One thread's blocking does not stop the others. Ideal for application requiring parallel processing. The OS can manage and schedule threads efficiently. Cons: creating a kernel thread for every user thread consumes more resources. The number of threads is often limited by the system resources. Frequent thread creation and destruction can affect the performance.
This is Shravanti. I'm going to explain about two-level model definition. The two-level model combines features of both many-to-one and one-to-one models. It allows multiple user threads to be mapped to a smaller or equal number of kernel threads. In this diagram, it is similar to many-to-many model, but we can map a specific user thread to a kernel thread. Here are the pros and cons. Pros: It's highly flexible because it can handle simple threads and critical threads simultaneously. It achieves true parallelism, meaning multiple threads can genuinely run at the exact time on different CPU cores. Cons: it's complex for the operating system to implement because it has to manage two different mapping schemes. This complexity leads to higher overhead in managing, scheduling, and synchronizing all the threads. Here are the real world applications: transaction processing and web applications. Transaction processing. Systems like banking and online shopping use multi threading to handle millions of simultaneous transactions quickly and without errors. Web or internet applications. When thousands of users connect to a web server at once, threads allow the server to handle multiple client requests concurrently, improving responsiveness and efficiency. Banking and telecom systems. Banking. Threads manage things like online fund transfers, balance updates, and background verification tasks simultaneously. They prevent the entire system from slowing down during high traffic. Telecom. When millions of users make multiple recharge or service requests, multi-threading process them concurrently, ensuring quick response times and smooth functionality. Multi-threading is vital for modern software, making applications faster and more responsive. Here is the comparison table for your reference. Thank you.